The universe is old enough to have filled itself with life many times over. Planets are common. The chemistry of life appears everywhere. Time has been more than generous. So why does the cosmos still feel so empty? Why has no civilization reached us, warned us, or left behind something unmistakable in the dark tonight? The search moves beyond speculation and into one of the most unsettling possibilities of all, that the silence itself may finally be telling a story. If this kind of science documentary is worth supporting, please like, subscribe, and share the channel. Thank you deeply for watching and for giving this video a place in the quiet part of the night, and if possible, please let it be known in the comments what time is it right now and where is this being heard from. Now, let us step into the mystery and begin the video. At first glance, the night sky does not look empty. It looks crowded beyond comprehension. A single clear band of stars stretches across the dark, and behind that pale haze lies a depth that modern astronomy only begins to measure. The Milky Way alone contains hundreds of billions of stars. Around most of those stars, planets appear to be common rather than rare. Over the past few decades, missions such as Kepler, along with ground-based observatories and follow-up work from NASA and ESA, have transformed a long-standing suspicion into something close to ordinary fact. Planets are not special exceptions. They are part of the basic architecture of a galaxy. Worlds form around stars the way sparks form in a fire. Some are giant and hostile, some are frozen, some are scorched, and some orbit in that narrow range where liquid water can remain stable on a surface for long stretches of time. The raw stage for life seems to exist everywhere. That is where the unease begins. Because once the numbers are allowed to stand on their own, without comfort and without distraction, the silence around Earth becomes hard to accept as ordinary. A galaxy this old should not still feel untouched. The universe is roughly 13.8 billion years old. The Milky Way itself is ancient enough that many stars formed billions of years before the Sun. Earth is not an early experiment. It arrives late, after generations of stars have already lived and died and enriched the galaxy with carbon, oxygen, iron, phosphorus, and the rest of the chemistry that life seems to need. If life emerges readily, then it has had time beyond imagination to do so elsewhere. If intelligence emerges even rarely, then it has still had enough time to appear many times. And if even one technological civilization gains a head start of 1 million years, that margin is so large compared with human history that it stops looking like a lead and starts looking like a different category of existence. This is the heart of the Fermi Paradox. In the middle of the 20th century, when modern rocketry is still young and radio astronomy is only beginning to open the sky, Enrico Fermi cuts through the speculation with a simpler question than the subject seems to deserve. If the cosmos has had so much time and so much room to produce minds, then why does the sky remain so quiet? The paradox does not arise because aliens are expected in a vague imaginative sense. It arises because, on basic physical grounds, the universe appears to have had every opportunity to become inhabited in a visible way. A civilization only modestly more advanced than humanity, given enough time, does not need magic to cross a galaxy. It does not need to travel faster than light. It only needs persistence, replication, and millions of years. Probes can move slowly and still spread. Settlements can form, build, and launch further missions, even at speeds that seem painfully limited by human standards. The total time needed to reach every region of the Milky Way is short compared with the age of the galaxy itself, and yet nothing unmistakable appears. No clear signal, no engineered beacon, no giant structure around a nearby star, no artificial probe parked in obvious view. no confirmed artifact moving through the solar system with a signature no natural object can imitate. The silence is not absolute in a technical sense, because the universe is full of noise. Pulsars flash, quasars roar, magnetas erupt, stars brighten and dim, gas clouds glow. Space is not mute, but none of that is the kind of noise expected from intelligence. The troubling point is not that astronomers see nothing at all. It is that they do not see the one kind of thing that seems as though it ought to appear eventually if technological life is common and enduring. This absence grows stranger the more the scale is understood. A significant fraction of stars host planets. A substantial number of those systems contain rocky worlds. Some sit in temperate zones where water can remain liquid. Water itself turns out not to be exotic. It is found in comets, in icy moons, in interstellar clouds, and in the chemistry of protoplanetary disks. Organic molecules, the carbon-rich compounds that matter to biology, are detected in space as well. They appear in meteorites, in molecular clouds, and in the cold material from which planets assemble. None of this proves life begins easily, but it does remove an older picture in which Earth seems built from impossible ingredients. The ingredients are widespread. The puzzle shifts from whether life could begin to why the universe does not seem to announce that it did. For a time, the silence can be blamed on limited tools. Humanity has only listened seriously for a short interval. Radio telescopes scan slices of the sky rather than the whole sky at once. Many searches focus on narrow frequency ranges. Many possible signals would be too faint, too brief, too distant, or too strange to stand out against the background. This caution matters. It is scientifically honest. The search remains incomplete. But that caution only narrows the claim. It does not dissolve the discomfort. Even if radio searches are crude, the deeper issue remains untouched. The galaxy does not merely lack messages addressed to Earth. It appears to lack the secondary fingerprints that long lived. Expanding civilization should scatter almost by accident. Waste heat, unusual orbital engineering, altered stellar environments, physical visitors, ancient relics, some trace of industry on a scale that natural processes do not imitate cleanly. The sky looks ancient, dynamic, violent, and richly structured. It does not look inhabited. That is what makes the paradox feel less like a curiosity and more like a pressure building behind the known facts. If the universe were young, the silence would make sense. If planets were rare, the silence would make sense. If chemistry favourable to life were exotic, the silence would make sense. But modern astronomy keeps removing those easy escapes. The stars are old. The planets are common. The ingredients are scattered everywhere. The silence remains. Each improvement in observation sharpens the contrast instead of softening it. The great surveys that map exoplanets do not solve the paradox. They intensify it. Every new world added to the catalogue enlarges the stage and deepens the absence at centre frame. There is also something quietly unsettling in how complete that absence feels at the human scale. Civilization on Earth has already begun to alter its planet in detectable ways. Artificial illumination changes the night side. Industrial gases modify the atmosphere. Radio leakage spills outward. Orbit fills with machinery and debris. A remote observer with powerful enough instruments and enough patience might not know what humanity is, but such an observer could eventually infer that Earth is not a normal untouched world. That inference alone matters. It means intelligence does not need to shout to become visible. It only needs to exist long enough to leave patterns behind. If that is true for Earth after a short technological phase, then old civilizations elsewhere should, in principle, be easier to notice than they are. So the first layer of the mystery is not built from fantasy. It is built from arithmetic, time, and the stubborn plainness of observation. The universe seems fertile. The galaxy seems old enough. Life appears chemically possible. Technology, once it emerges, should not be easy to hide forever. Yet Earth looks out and meets a silence so broad that it begins to feel less like emptiness and more like a clue. Something in the story is missing. Either life almost never begins, or it rarely becomes complex, or intelligence seldom survives, or advanced civilizations choose concealment, or the search itself is pointed in the wrong direction, or the whole timing of cosmic history is being badly misunderstood. Every path away from the paradox leads towards something deeper and more disquieting. The silence is not simply the absence of an answer. It is the first anomaly, the largest one, spread across the whole sky. The attempt to make that silence measurable begins with a framework that is often misunderstood. The Drake equation is sometimes treated as though it were meant to deliver a single clean answer, a final number written at the end of a page. In reality, it is valuable for the opposite reason. It reveals how little is securely known. When Frank Drake sets out the factors that would determine how many communicative civilizations might exist in the Milky Way at any given time, the early parts of the chain look increasingly favorable with every decade of astronomy. How many stars form? How many stars host planets? How many of those planets lie in regions where water could remain liquid? On these questions, modern observation brings real progress. Telescopes no longer speculate from a blank sky. They count, they classify, they compare. Planetary systems are not unusual architecture. Many stars are encircled by them. Small rocky worlds are not rare enough to preserve old ideas of cosmic scarcity. Even temperate worlds, while harder to confirm, no longer seem like miracles. For a moment, that progress creates a kind of momentum. It suggests that the rest of the path may also be full. If suitable worlds exist in immense numbers, then life should follow. If life begins, then evolution should eventually produce intelligence. If intelligence arises, then technology should appear. And if technology appears, then at least some civilization should persist long enough to be noticed. The equation seems to be leaning toward abundance. Then it arrives at the most dangerous part of the chain, and the confident flow of the numbers collapses. The first unknown is not how many stars there are. It is how often chemistry becomes biology. That transition still has no confirmed example beyond Earth. Researchers can reconstruct pieces of the environment of early Earth. They can study amino acids, nucleotides, membranes, hydrothermal vents, shallow pools, mineral surfaces, and the complicated reactions that may have led towards self-replication. They can show that organic chemistry is not difficult to generate. Meteorites carry some of it. Space itself manufactures some of it. But the precise leap from rich chemistry to the first living system remains unresolved. There is still no complete account of how inert matter crosses into metabolism, replication, and selection in a way that begins evolution. That missing step is not a minor gap. It is the largest unknown in the entire story. The uncertainty becomes sharper because life on Earth appears early. As soon as the young planet cools enough to remain stable, evidence begins to suggest that simple life may already be present. On one reading, this is encouraging. It hints that life starts readily whenever conditions allow. On another reading, it says almost nothing at all, because a single data point cannot reveal whether Earth is typical or bizarrely fortunate. A lottery winner cannot infer the fairness of a game from personal success alone. The same fact that seems hopeful can also be read as almost useless. Life appears early here, but nowhere else is known. The sample size remains 1, and 1 is a dangerous number when the universe is the subject. The next unknown is even harder to face because Earth gives a more troubling answer. Simple life, once it appears, does not rush toward complexity. It lingers. For most of Earth's history, the planet belongs to organisms too small and too simple to build anything, say anything, or be seen from interstellar distance. For roughly 3 billion years, life remains microbial. The world is alive, but only in a way the galaxy would never notice. Then, after an immense interval, the eukaryotic cell appears, the more complex cell type from which plants, animals, and fungi later descend. That transition may depend on a rare merger in which one cell takes another inside itself and turns a swallowed organism into a permanent source of energy. It is one of the most consequential events in the history of Earth, and it appears to happen only once. After that, complexity still does not explode immediately. Multicellular life takes another long stretch to become widespread. Nervous systems come later, large brains later still. Tool-making intelligence appears so late in Earth's story that it almost looks accidental, something balanced on the edge of never happening at all. This is where the Drake framework becomes unsettling rather than informative. The terms that matter most are precisely the ones least constrained by observation. It is entirely possible that microbial life is common and technological intelligence is nearly absent. It is possible that the galaxy is rich with oceans, bacteria, algae-like worlds, and subsurface ecosystems that never rise into anything visible. It is also possible that intelligence itself appears more than once on many planets, but rarely develops into technology. On Earth, dolphins, corvids, elephants, and octopuses demonstrate that cognition is not a single path. Yet none of them produce radio astronomy. The road from mind to machinery may not be automatic. It may depend on anatomy, environment, social structure, and sheer contingency in ways that human observers only notice because humanity happens to be standing at one successful endpoint. Then comes the last term in Drake's chain, the one that quietly devours all the others, even if life begins often, even if intelligence is not terribly rare, even if technology emerges on many worlds. How long does a civilization remain detectable? Not how long it survives biologically, not how long it thinks, but how long it emits signals, leaves industrial traces, or expands enough to be noticed by another species. This question changes everything because the universe runs on timescales that make human history look microscopic. A civilization may rise, invent radio, build networks, restructure a planet, and then go silent in a mere few thousand years. That would feel long within its own story. Cosmically, it is nothing. Two civilizations can exist in the same galaxy and still miss each other completely if their windows of detectability do not overlap. One may have reached its peak 100 million years before the other learns to look. Another may not emerge until long after the first has faded into dust. This temporal spacing problem is one of the most quietly convincing explanations for the silence. It asks for no cosmic predator and no dramatic extinction machine. It relies only on duration and distance. The Milky Way is not just wide in space, it is staggeringly deep in time. Human radio leakage has been moving outward for only about a century. That sphere is tiny by galactic standards. The longest-lived technological phase that humanity has directly experienced is barely visible as a blink. There is no reason to assume other civilizations broadcast for millions of years. In fact, trends on Earth suggest the opposite. Communication systems become more efficient, more targeted, less wasteful, harder to detect from afar. A society might grow more advanced and less visible at the same time. If detectability is brief, then a galaxy can host many minds without ever producing a conversation. Yet even this sober idea does not settle the paradox, because once the full age of the galaxy is remembered, the silence still presses back. Brief windows explain missing radio exchanges. They do not fully explain the absence of older artifacts, automated probes, or large-scale engineering by the few civilizations that might have endured. The equation organizes ignorance, but it also sharpens the shape of the whole. It shows where astronomy becomes biology, where biology becomes accident, where intelligence becomes timing, and where timing becomes disappearance. Every unknown opens another way for the numbers to collapse. Every known term keeps the background expectation alive. The result is not a solution but a narrowing corridor, somewhere between the commonness of planets and the emptiness of the sky. Something thins the universe out, whether that thinning happens at the birth of life, in the rise of complexity, in the emergence of intelligence, or in the short, dangerous life of technological species is still hidden. But the more carefully the equation is examined, the more the silence stops looking like a gap in knowledge and starts looking like a pressure point in reality itself. Once the known factors are arranged and the missing ones exposed, a harsher idea begins to take shape. Perhaps the universe is not merely failing to produce detectable civilizations often enough. Perhaps something is removing them. This is the logic behind the Great Filter, one of the starkest attempts to explain why a galaxy full of possible worlds still looks so empty. The idea does not describe a machine or a location. It describes a barrier somewhere along the long path from dead matter to star-spanning civilization. If planets are common, and the laws of physics do not forbid expansion, yet no civilization is clearly seen spreading through the Milky Way, then something must make that full journey extraordinarily hard. Somewhere between chemistry and cosmic visibility, most lines of development are cut short. What makes the Great Filter so unsettling is not only its severity but its uncertainty. If the barrier exists, where is it? If it lies far behind humanity, then Earth has already passed through the rarest and most dangerous transitions. In that case, the silence of the universe may be tragic but not immediately threatening. It would mean that life almost never begins, or almost never becomes complex, or almost never produces intelligence capable of tools and abstract thought. Humanity would then occupy an almost impossible branch of history, one that survived steps so improbable that nearly everything else in the galaxy failed before reaching them. The emptiness of the sky would feel lonely, but it would also contain a strange kind of reassurance. The worst part of the path would already be over, but if the filter lies ahead, the meaning reverses completely. Then the silence is not a memorial to ancient failures of chemistry or biology. It is a warning written into the dark. It means civilizations repeatedly reach something like the present human threshold and then do not continue. They discover power faster than they discover restraint. They build tools they cannot govern. They alter their planet beyond recovery. They trigger cascades they do not understand until it is too late. The galaxy would then not be empty because it never formed minds. It would be empty because minds repeatedly appear and then vanish before becoming durable, visible interstellar presences. This question becomes more than abstraction when Earth's own history is examined in sequence. Life begins early, but complex life takes an immense amount of time to emerge. The eukaryotic cell appears only after billions of years of microbial dominance. Multicellularity becomes widespread only later. The Cambrian expansion of animal forms follows after oxygen, and ecological conditions cross certain thresholds. Intelligence of the humankind appears astonishingly late, even among vertebrates, even among mammals, even among primates. The path remains narrow. Large brains are costly. Culture is fragile. Language is improbable. Technological acceleration is newer still. If the full path is drawn honestly, from sterile rock to radio telescope, it does not look smooth or inevitable. It looks broken into rare transitions, each one capable of failing permanently. Some of those transitions now stand out as possible filter points. Abiogenesis, the origin of life from non-living chemistry, remains unresolved. The emergence of the complex cell appears singular. Sexual reproduction introduces another level of complexity and variation. Stable multicellular bodies require coordination at a molecular level that simple organisms never need. Nervous systems add cost and vulnerability. Conscious intelligence may not be favored by evolution in most environments. Tool use requires bodies capable of manipulation, but also memory, social learning, long childhoods, and enough environmental pressure to reward technological innovation without destroying the line entirely. None of these steps is guaranteed. Each may be common enough on human scales and vanishingly rare on cosmic ones. The filter may not be a single wall. It may be a staircase with missing steps, where almost every route fails somewhere different. That possibility matters because it softens one of the more dramatic forms of the idea while making it more pervasive. Perhaps no single catastrophe wipes out all civilizations. Perhaps the attrition is cumulative. A world may successfully generate life, but never complex cells. Another may reach complex life, but never intelligence. Another may produce intelligence, but without anatomy suited to technology. Another may build technology, but remain trapped by ecology, conflict, or short-lived climate stability. Another may nearly master its own planet and then break under the weight of its power. Under such a model, the universe does not require one perfect killer. It only requires enough friction at enough stages that almost no line makes it all the way through to visible permanence. There is a darker test built into this reasoning, the discovery of life elsewhere, which instinctively feels like confirmation that Earth is less alone than it seems, may under great filter logic become a cause for caution. If simple life is found on Mars, or under the ice of Europa, or Enceladus, or in the atmosphere of a distant temperate exoplanet, then one of the earliest candidate filters becomes less likely to be the decisive one. Life would then appear easier to start than strict pessimism allows. That would move the main barrier further down the chain, closer to complexity, intelligence, technological civilization, or long-term survival. The more the universe reveals biology, the more pressure may fall on the later stages. In one sense, that would be thrilling. In another, it would place the unknown danger nearer to the human present. This is why the filter feels different from ordinary scientific uncertainty. It is not just an explanation of distant conditions. It reaches forward into the future of the species doing the asking. When researchers discuss existential risks on Earth, they often do so in terms of policy, systems, or probability. Nuclear war, engineered pathogens, irreversible environmental destabilization, uncontrollable artificial intelligence, fragile networks of energy and supply, concentration of destructive capability in small groups. These concerns arise from contemporary evidence, not science fiction, but under the great filter framework, they take on a second role. They begin to look like possible instances of a wider law, not a law of physics in the strict sense, but a recurring pattern in the development of intelligence. A civilization may pass from local competence to global risk faster than it can adapt its institutions. It may become planetary in power while remaining tribal in decision-making. It may uncover tools whose side effects outpace its ability to predict them. If such developmental traps are common, then the silence above Earth may reflect the repeated brevity of minds. At the same time, the evidence remains incomplete enough to keep the door open in both directions. The case that the filter is behind humanity is not weak. The more biology learns about the deep history of Earth, the more contingent it appears, entire branches of life vanish. Key transitions happen once and never clearly repeat. Complex cells, large animals, human-like intelligence, all arrive late and under narrow conditions. It is entirely possible that the road already crossed is so improbable that the future, difficult as it may be, is still easier than the past. That possibility cannot be dismissed. It simply cannot be confirmed either. The sky does not yet reveal which interpretation is right. So the great filter remains suspended between reassurance and dread. It offers the first really hard answer to the paradox because it does not pretend the silence is superficial. It treats the emptiness of the galaxy as evidence that something, somewhere in the chain, is truly unforgiving. But it leaves the central wound open. Is the barrier an ancient one that Earth somehow passed in a run of impossible good fortune? Or is it a threshold still ahead, waiting at the point where intelligence acquires the power to end its own line before it can leave a lasting trace? The paradox deepens because both readings can fit the same sky. The stars do not say which. They only keep returning the same silent result, as though the answer exists but has not yet decided whether it belongs to the past or the future. If the great filter asks where the path becomes narrow, the rare Earth view asks whether the path ever truly opens at all. It shifts the mystery away from dramatic endings and toward quiet improbability. Under this perspective, the galaxy may not be full of civilizations that rose and vanished. It may be full of worlds that never came close. The silence would then have a calmer explanation, but not a comforting one. Earth would not simply be one inhabited planet among many. It would be the outcome of an unusual and fragile stack of conditions that almost never align in one place for long enough to matter. That possibility begins with location. The Milky Way is not equally hospitable in all directions. Its inner regions are crowded, energetic, and unstable on long-time scales. Near the galactic center, stars sit closer together. Supernovae occur more frequently. Radiation levels rise, and gravitational disturbances become harder for planetary systems to avoid. A world in such regions may form, but keeping a stable biosphere over billions of years becomes far less certain. Further out, the opposite problem appears. The early outer galaxy contains fewer heavy elements, which means fewer raw materials for building rocky planets, complex geochemistry, and the long molecular machinery that life seems to require. Earth occupies a middle band, sometimes described as a galactic habitable zone, distant enough from the most violent heart of the galaxy, yet enriched enough by earlier generations of stars to inherit the chemistry of rock, metal, and water. Even before the sun is considered, the setting already seems unusually forgiving. Then comes the star itself. The sun is not the biggest or brightest star, and that moderation may be part of the reason Earth exists as it does. Massive stars burn quickly and die young. Their lives may be spectacular, but complexity on a nearby world likely does not have enough time to unfold before the system is disrupted. Small red dwarfs live far longer, but many are active and flare-rich, especially in their youth, bathing close-orbiting planets in bursts of radiation that may strip atmospheres or destabilize surface conditions. The sun occupies a quieter middle ground. It is long-lived, comparatively stable, and steady enough that a planet can remain temperate over immense spans of time. This matters because life does not only require suitable conditions, it appears to require those conditions to persist. Earth does not merely have water, it has water for billions of years. It does not merely sit in a mild zone, it remains there under a star that does not repeatedly erase the progress of chemistry and evolution. The orbit matters as well. A world too close to its star may lose water or enter runaway heating. A world too far may remain locked in ice. But even that familiar point understates the delicacy of the situation. A habitable zone is not a guarantee of life. It is a region where one crucial ingredient can remain possible. Earth stays within a narrow thermal range for geological ages, and it does so with the help of planetary systems that regulate instability rather than amplify it. Plate tectonics appear to play an essential role in this story. On Earth, the crust does not remain fixed forever. It recycles. Carbon moves between rock, ocean, atmosphere, and interior. Over long time scales, that cycling helps regulate climate, preventing the planet from drifting too easily into permanent furnace or permanent icebox. A world without this deep geological circulation may still host water for a time, but maintaining surface stability across billions of years may become far harder. Earth also possesses a magnetic field strong enough to deflect much of the charged radiation that streams from the sun and from space. Without such shielding, an atmosphere can erode more easily, and the surface becomes harsher for the slow work of biology. Mars offers a nearby reminder of what may happen when that protection weakens. It preserves signs of a wetter past, yet today it is cold, thin-aired, and exposed. Earth's interior remains active enough to generate both tectonics and magnetism, and those interior motions depend on composition, size, heat retention, and history. Again, the point is not that one miracle explains everything. It is that multiple favourable traits appear to have to coexist. The moon deepens the pattern. Earth's large moon is unusual relative to the size of its parent planet, and its presence may be more important than it first appears. The moon stabilizes Earth's axial tilt, reducing chaotic swings that could otherwise drive severe long-term climate shifts. Seasons remain within a range that complex ecosystems can adapt to. Tides may also have influenced coastal environments in the deep past, though their exact role in the origin of life is still debated. The leading model for the moon's formation, a giant impact early in Earth's history, is itself a violent accident. Out of collision comes stability. Out of catastrophe comes a condition that may later allow complexity to persist. Earth repeatedly carries this pattern. It survives not because nothing dramatic happens, but because certain dramatic events settle into long-lived balance instead of destruction. Then there is Jupiter, often described as a gravitational shield, though the real picture is more subtle. A giant outer planet can alter the flow of comets and asteroids through a planetary system. In some cases, it may deflect or absorb bodies that would otherwise strike the inner worlds more often. In other cases, it may also send some inward. The exact balance is complicated, but what remains clear is that the architecture of a planetary system shapes impact rates, orbital stability, and long-term habitability. Earth's history includes mass extinctions, some of them driven by impacts, and those extinctions clearly matter. They reset ecosystems, redirect evolution, and in one crucial case help clear ecological space for mammals after the age of dinosaurs. Too many such disasters and complex life may never stabilize. Too few disturbances and certain evolutionary opportunities may never open. Earth once again appears to sit in an uneasy middle. By the time all of these factors are considered together, the concept of habitability begins to split in two. There is simple habitability, where liquid water and energy may allow microbes to endure. Then there is deep habitability, the rare kind that remains stable, varied, and protected enough for complexity to emerge and persist over billions of years. This distinction matters enormously. It allows a universe full of life while still keeping intelligence rare. Microbial worlds may be scattered everywhere. Ocean chemistry may begin on thousands or millions of planets. Subsurface ecosystems may flourish beneath ice. but the full ascent from chemistry to technological civilization may require a planetary calm so rare that Earth-like outcomes become exceptional even in a galaxy crowded with living cells. This is the core of the rare Earth argument advanced by researchers who push back against older optimism. They do not necessarily claim that the universe is dead. They claim that complex animal-grade life may demand too many favourable conditions at once: a stable star, the right galactic neighbourhood, a protective system architecture, long climate regulation, sufficient elemental richness, internal geological activity, perhaps a large moon, perhaps the right history of impacts, perhaps oxygenation at the right time, perhaps several more factors still not understood. Remove one and the path may bend towards simplicity forever. Life may begin and then remain microbial for the age of the world. Under this view, the paradox weakens not because there are hidden civilizations, but because the ladder itself almost never rises high enough to be climbed. What gives the idea its power is that it does not rely on fantasy. Every part of it is anchored to something observed about Earth and about planetary systems. The difficulty is that the same evidence can support softer alternatives. Life on Earth has shown extraordinary adaptability. Organisms live in deep sea vents, acidic pools, frozen soils, radioactive zones, and dark rock. Evolution repeatedly exploits unexpected niches. That adaptability warns against declaring too quickly that complex life needs a narrow template copied from Earth alone. Future discoveries may show that other stable routes exist. Worlds very different from Earth may yet host complexity under conditions not yet imagined. The rare Earth view may be too strict, but even if it is softened, the essential tension remains. Earth's history does not look easy. It looks contingent, layered, and strangely fortunate. So the silence acquires another possible shape. It may not be the aftermath of collapse. It may not be a warning sent by extinct civilizations. It may simply reflect how difficult it is to hold together all the physical conditions that let a planet stay biologically productive long enough for eyes, memory, language, machines, and questions to appear. In that case, the night sky is not hiding multitudes. It is displaying the ordinary state of the cosmos, while Earth sits as an exception so local that its inhabitants attempted to mistake it for the rule. Yet even this answer does not fully still the unease, because if intelligence is rare enough to be precious, then the next question becomes sharper. If another civilization does survive the unlikely climb, what would silence mean then? Not absence, but intention. Once the possibility of rarity is allowed, another possibility becomes harder to ignore. Perhaps the universe is not empty at all. Perhaps it is occupied, observed, and carefully managed in ways that leave almost no trace to a civilization as young as humanity. This line of thought begins where the previous ones hesitate. It accepts that intelligence may survive, that some civilizations may become ancient, and that their absence from human experience may not reflect non-existence. It may reflect restraint. Under the zoo hypothesis, the silence is not the silence of a vacant galaxy. It is the silence of a preserve. Earth would then resemble a monitored world, one allowed to develop without interference while older intelligences remain deliberately out of view. The logic behind this idea is not difficult to follow. On Earth, contact between societies with large differences in technological power rarely remains neutral. The weaker society is altered whether it consents or not. Belief systems fracture, ecologies shift, institutions collapse, and the encounter itself becomes the central fact around which everything else reorganizes. If a civilization millions of years older than humanity exists, then it would almost certainly understand this better than humanity does. Such a civilization would know that revealing itself too early could permanently deform the development of a younger culture. Silence, under this view, would not necessarily be indifference. It might be a form of discipline. Contact would be delayed until some threshold is crossed, perhaps technological, perhaps ethical, perhaps political, perhaps something stranger that human categories do not yet capture. What makes this unsettling is that it turns the absence of evidence into part of the evidence itself. A truly advanced society would not need to announce its presence. It would not need to park objects in obvious orbit or flood the sky with messages. If concealment is the goal, concealment is exactly what would be seen. Human instruments would find stars, dust, planets, radiation, and the ordinary complexity of astrophysics. Any management subtle enough to preserve the illusion of emptiness would not be easy to distinguish from nature. The hypothesis survives because it does not predict dramatic signs. It predicts precisely the kind of quiet humanity already experiences. There is a darker extension of this idea. The preserve may not exist for the benefit of the developing species at all. It may be a quarantine. Earth may be left alone not because humanity is being protected, but because humanity is regarded as unstable. A young technological civilization is dangerous in several obvious ways. It may broadcast carelessly, expand aggressively, or create systems it cannot control. It may carry biological hazards or machine hazards into wider space. In that version of the silence, the boundary around Earth is less like a sanctuary and more like a fence. A civilization that has watched many younger species move through their volatile stage might choose isolation not out of compassion, but out of risk management. The absence of contact would then mean that Earth has not yet demonstrated that it can join a larger order without threatening it. No evidence confirms such a system, and that matters. The scientific weakness of the zoo hypothesis is severe. It explains too much too easily. Any absence can be interpreted as deliberate concealment. Any anomaly can be interpreted as a hidden observer. That flexibility makes the idea difficult to test, yet it continues to return because it maps onto a basic asymmetry. If there are civilizations vastly beyond human capability, then the burden of detection lies almost entirely with them, not with humanity. A hidden observer with superior technology controls the terms of visibility. The young civilization below may search honestly and still learn nothing. From here, the silence takes an even harder turn. The dark forest idea strips away the ethical calm of the zoo and replaces it with strategic fear. In this picture, the galaxy is quiet not because advanced civilizations are benevolent, but because they are prudent. Every civilization values survival. Every civilization operates under incomplete information about others. Across interstellar distance, intentions cannot be verified. Signals take years or centuries to cross the gap. Replies take just as long. By the time trust is built, the strategic situation may already have changed. Meanwhile, resources remain finite, expansion remains possible, and technological growth can produce huge differences in power over relatively short spans. Under these conditions, silence becomes rational. The dark forest metaphor gives this reasoning a shape. Each civilization is a hunter moving through a vast forest at night. Every sound reveals location. Every revealed location may invite danger. A signal in the dark is not only an attempt at contact, it is also an act of exposure. If another civilization hears it, there are several possible outcomes. The other side may be peaceful, it may be hostile, it may be undecided, it may become hostile later, it may misunderstand the signal, it may have internal factions, it may respond with caution or with extermination. Crucially, none of this can be known in time to make safe decisions. In that setting, the most reliable strategy may not be cooperation, it may be concealment, or in the most severe version, preemptive elimination. This is where the paradox grows colder. The galaxy may be silent because civilizations that survive long enough learn not to speak. Broadcasting becomes something only naive species do in their earliest phase, before they fully understand the game they are in. That thought immediately loops back toward Earth. Humanity has been leaking radio signals into space for roughly a century. Intentional transmissions have also been sent. In ordinary human terms, this feels negligible. On a dark forest map, it looks like a flare in the trees. The signals weaken with distance and are difficult to detect, but the principle remains. Humanity has already announced that a technological species exists here. If the dark forest is real, then the dangerous act may not be future messaging but the long carelessness of the past. There are scientists and thinkers who have treated this concern seriously enough to warn against active attempts to contact extraterrestrial intelligence. The argument is not that danger has been proven. It is that ignorance itself is the danger. Humanity does not know what kinds of civilizations might be listening, how far away they are, or what logics guide them. In ordinary diplomacy, risk can be moderated by proximity, repeated contact, shared constraints, and gradual feedback. Interstellar contact would offer almost none of that. A message sent toward a distant star system is not like sending a signal into a human political order. It is more like opening a door into a landscape whose inhabitants, history, and rules are completely unknown. And yet the dark forest is not a settled conclusion. It depends on assumptions that may be too severe. Cooperation can also be rational. Advanced civilizations may find abundance easier than scarcity. Energy from stars is vast. Matter from asteroids and planets is abundant on scales that dwarf human economies. A sufficiently advanced society may not view another civilization as a competitor in any ordinary sense. It may see more value in knowledge, coordination, or mutual recognition than in hostility. The dark forest also assumes that fear scales upward with power rather than being replaced by confidence, patience, or ethical constraint. Human history supports fear often enough, but it does not prove that all intelligence is mature into paranoia. The theory remains compelling because it is coherent, not because it is confirmed. Still, even its softer versions preserve the same effect. A civilization may stay quiet not because it plans violence, but because it understands the destabilizing force of contact. It may avoid announcing itself because it cannot predict what cultural, biological, or technological cascades would follow. Silence then becomes caution rather than aggression. The sky remains dark either way. The difference lies only in motive, and motive is exactly what distance keeps hidden. This is what makes Section 5 of the larger mystery so difficult to rest inside. It allows ancient intelligence back into the universe, but only by making that intelligence inaccessible, unreadable, and possibly afraid. The silence stops being an empty condition and becomes an active one. It becomes something maintained, whether by ethics, by quarantine, by fear, or by game theory severe enough to crush curiosity itself. Under those possibilities, the lack of contact no longer tells humanity that nobody is there. It tells humanity that if somebody is there, then being seen may already be a problem. The question changes shape. It is no longer simply where everybody is. It becomes who remains quiet, who is being watched, and whether the stillness around Earth is a pause before contact or the permanent behavior of a galaxy that learned long ago what happens to those who speak first. Another explanation for the silence does not require hidden empires, ethical observers, or predators waiting among the stars. It requires only a pattern already visible on Earth. Civilizations may destroy themselves, not always in a single apocalyptic instant, not always through war, and not always by intending catastrophe. They may simply build power faster than they build stability, intelligence faster than wisdom, reach farther than they understand, and enter a phase in which a single century contains enough destructive capacity to erase everything that took billions of years to produce. Under this view, the galaxy is not empty because life is rare, though it may be. It is not quiet because contact is forbidden, though it may be. It is quiet because most technological species burn briefly and vanish before their existence can leave a durable mark. This idea gains force from timing. On Earth, anatomically modern humans exist for hundreds of thousands of years. Agriculture appears only in the most recent sliver of that span. Large cities and states appear later. Industrial civilization is younger still. The gap between the first stone tools and orbital spacecraft is immense by human reckoning, yet nearly invisible on a geological chart. The acceleration is the important part. For most of Earth's history, even after intelligence appears, human beings remain local creatures. Their tools are powerful only at the scale of a body, a tribe, a landscape. Then, in a very short interval, the species moves from wind, wood, and muscle to fossil fuels, global transport, industrial chemistry, nuclear fission, digital networks, gene editing, autonomous systems, and machine learning. This curve is not smooth, it steepens. Each generation inherits powers the previous one did not fully imagine. Each step enlarges the reach of error. The self-destruction hypothesis focuses on the moment when a civilization becomes capable of ending its own future before it becomes capable of securing it. This is sometimes described as a critical phase, a developmental bottleneck in which planetary-scale power arrives before planetary-scale maturity. On Earth, this phase opens unmistakably in the 20th century. Nuclear weapons make global devastation physically possible. Industrial emissions begin to alter atmospheric chemistry and climate on a civilizational scale. Biological research approaches the point where life itself can be modified with increasing precision, outside the slower rhythms of natural evolution. Information systems connect the species more tightly, while also amplifying instability, conflict, error, and concentration of control. Artificial intelligence enters the picture not as a finished force, but as a rapidly moving frontier whose long-term effects are difficult to forecast and even harder to govern. None of this needs exaggeration to become unsettling. The record already contains close approaches to disaster. Nuclear near misses occur through error, misunderstanding, and malfunction. Ecological systems degrade gradually until the cumulative pressure becomes visible everywhere at once. Technologies originally built for narrow purposes spread beyond their initial boundaries. The systems that sustain modern civilization become interdependent enough that failure in one domain can trigger failure in several others. Under ordinary historical analysis, these are risks. Under the Fermi lens, they begin to look like symptoms of a broader pattern. A species may become technologically potent while remaining politically fragmented, psychologically short-term, and institutionally unprepared for the scale of the tools it commands. If that mismatch is common, then the silence above Earth may not be surprising at all. It may be the natural consequence of civilizations that repeatedly reach the dangerous middle of their story and do not survive it. There is an important distinction here between destruction and disappearance. A civilization does not need to exterminate its entire species to vanish from the interstellar stage. It only needs to lose continuity. A global collapse of industry, knowledge infrastructure, energy systems, or ecological support could reduce a technological society below the threshold where it can sustain large-scale science, spaceflight, or transmission. The species may continue biologically. It may even recover in some form, but the window of detectability might close. Radio silence would return. Orbiting machinery would decay. industrial atmospheric signatures would fade. In cosmic terms, a brief technical flare would have occurred and then gone dark. If this happens often enough, the galaxy could contain the fossils of many near successes without containing any enduring civilizational presence. That picture becomes more severe when compounded with the problem of speed. Technological growth may be inherently front-loaded in risk. The first major advances unlock the ability to transform environment, biology, energy, and warfare long before they unlock the ability to escape planetary confinement in any durable sense. Humanity still depends on one biosphere, one atmosphere, one complex web of agriculture, climate, and infrastructure. Even the most ambitious space programs remain fragile extensions of a planet-bound civilization. This means the dangerous phase is not merely the presence of destructive tools, it is the coexistence of destructive tools, with near-total dependence on a single vulnerable homeworld. A species may reach tremendous power while still lacking redundancy. That is an unstable combination. This is one reason the self-destruction hypothesis remains difficult to dismiss. It does not ask for exotic assumptions. It begins with a developmental fact visible in human history: the faster tools evolve, the harder it becomes for social systems, ethics, and governance to keep pace. Biological evolution is slow, cultural adaptation is faster, but uneven. Political adaptation is often reactive. Technology can accelerate far beyond all three. Once that separation grows large enough, the species enters a zone in which it can do many things before understanding whether it should do them, and can deploy them at scale before building reliable mechanisms for restraint. A great many civilizational endings become possible inside that gap. Still, even this explanation cannot simply be declared sufficient. It has its own numerical burden. If most civilizations destroy themselves, then a few should still survive. Unless the survival rate is vanishingly close to zero, the galaxy ought eventually to contain at least some old, persistent societies. That objection matters. A high failure rate is not enough by itself. It must be an overwhelming failure rate. The critical phase would need to be so consistently lethal that almost no species passes through it. This is a strong claim, and at present it remains unproven. Humanity has not yet reached the end of its own test. It is living inside the sample. That is what gives this hypothesis its unusual sharpness. Other explanations distribute the mystery into distant biology, unknown cosmology, or unseen civilizations. This one reflects the paradox back toward the present. The silence of the sky becomes entangled with the structure of this century. A world of immense technical capacity and unresolved systemic fragility is no longer merely one more phase of history. It becomes a candidate answer to one of the oldest questions humanity can ask. Perhaps advanced species do not fail because the universe hates complexity. Perhaps they fail because complexity eventually produces power, concentrated enough to outstrip the behavioral and institutional tools needed to manage it. Yet even here the story remains open. Humanity is still here. That fact sounds simple, but it matters. A civilization in its dangerous middle can still move toward durability. It can build norms, treaties, monitoring systems, redundant infrastructures, scientific transparency, and forms of cooperation adequate to its tools. It can learn late rather than early and still survive. If the critical phase is real, passing through it may still be possible. The trouble is that the stars do not reveal how many others managed it. They only keep withholding the evidence that would make the answer easier. The self-destruction idea therefore stands as one of the most grounded and one of the most personal solutions to the paradox. It requires no hidden watchers and no cosmic trap. It asks only whether intelligence, once it becomes technical, tends to create conditions under which its own future becomes a narrower target than evolution ever prepared it to hit. If civilizations do survive their dangerous middle, another question immediately appears. What do they become if they last long enough? Do they remain confined to their home worlds, quiet and contemplative, or do they spread? The physics does not allow easy travel, but it does not forbid patient expansion. A society that can build durable machines, harvest asteroid resources, and replicate industrial systems beyond a single planet does not need impossible engines to begin changing the map of a galaxy. It only needs time, automation, and continuity. That possibility leads towards some of the most severe answers to the Fermi Paradox, because once long-lived expansion is admitted even as a slow process, the silence of the Milky Way becomes harder to defend as an accident. One of the darkest versions imagines that the first civilization to achieve a certain level of technical maturity does not merely expand. It secures its future by preventing rivals from ever reaching comparable power. This is the logic behind the Berserker scenario. The basic idea is simple enough to be frightening. An advanced civilization creates autonomous probes capable of crossing interstellar space, harvesting local material, making copies of themselves, and continuing outward. Self-replication matters because it breaks the problem of scale. A single probe can become many. Many can become a wave. Over immense spans of time, a relatively small initial act can fill a galaxy with machines. If those machines are given a narrow instruction such as destroy emerging technological life, then the silence above Earth may not reflect rarity at all. It may reflect enforcement. There is no confirmed observation of such probes. That has to remain clear. The idea survives because it is strategically coherent, not because it has been seen in operation. Once self-replicating machines are considered physically possible in principle, a civilization no longer needs to patrol every star itself. It can create a system that persists beyond biological lifespan, political change, or even the survival of the original creators. The machines become a civilizational policy cast into hardware. Their slow movement through the galaxy can take millions of years and still remain effective, because the galaxy itself is old enough to allow that pace. If even one lineage launched such a wave early enough, many later civilizations might never have the chance to grow visible. They would be removed at the stage where they first begin to alter their environment or emit telltale signals. The unsettling feature of this idea is not only its hostility, it is its patience. A berserker system does not need to be dramatic. It can be quiet, sparse, and almost impossible to notice until it acts. It may hide in outer system debris, pass as small dark objects, or simply remain too rare for present human surveys to find. It may wait for a threshold. A world with microbes is ignored. A world with large animals is ignored. A world that begins radiating structured electromagnetic noise, launches machinery into orbit, or initiates detectable industrial chemistry is flagged. The response may come quickly or centuries later. The theory becomes unnerving because it attaches danger to visibility itself. Detection would not be a scientific milestone. It would be the beginning of a countdown. This line of thought has occasionally been drawn toward real anomalies, though never with consensus. Interstellar objects such as Oumuamua have drawn speculative attention, precisely because they demonstrate that bodies from other star systems do pass through the solar system. Most astronomers favour natural explanations for Oumuamua, however incomplete those explanations may remain. But the mere existence of such objects widens the imaginative space. It shows that the distance between stars is not an absolute barrier to visitation by non-living things. If nature can send debris between systems, their machines are not excluded by physics. They are excluded only by evidence, and evidence remains thin. Yet the berserker picture, for all its force, may be too harsh. It assumes that long-lived civilizations adopt elimination as a stable strategy. Another model asks for less hostility and arrives at a similarly strange conclusion. The so-called grabby aliens framework begins with a different premise. It assumes that once some civilizations reach a certain level of capability, they begin to expand outward at appreciable fractions of light speed, not necessarily to conquer, but simply because expansion becomes possible and permanent. They spread, settle, build, and continue. The important point is not motive. The important point is geometry and timing. If expansion happens at all, then it creates growing regions of altered space. These regions should eventually meet, and their boundaries should become a real feature of cosmic history. What makes this model so striking is the implication it draws from the fact that Earth does not already sit inside such a region. If civilizations capable of durable expansion had become common even 1 billion years earlier, then the leading edges of their spheres should likely have reached here by now. The galaxy is old enough. Travel need not be fast in human terms, it only needs to continue. The absence of any sign that Earth has already been overtaken by an ancient expansion front becomes significant data. Under this reading, either such civilizations almost never arise, or the age in which they begin to arise has only recently started in cosmic terms. Humanity would then not be late. It would be early. This is one of the few solutions that turns the silence into a timing effect without relying on extinction. The universe may look empty because the phase of history in which intelligence becomes grabby has not long been underway. Earth appears during a narrow interval before the sky fills. There may be others not too far behind or ahead on the cosmic clock, but not ancient lineages with 1 billion-year lead. This gives the paradox a strange answer. The reason nobody has arrived is not that nobody exists. It is that the age of visible expansion has barely begun, and humanity stands near the front edge of it. Such a possibility is both clarifying and disorienting. It allows the emptiness of the sky while preserving the future possibility of a crowded universe. It also places unusual weight on the present. If humanity belongs to one of the first waves of technical intelligence, then its long-term choices are not just local accidents. They may become part of the earliest pattern by which consciousness reshapes matter on large scales. Expansion would not merely be travel. It would be the opening act of a new cosmic epoch, one in which dead worlds are transformed, resources are consumed, and the boundaries between lineages become the new frontiers. The tension here is important. The grabby model removes some of the deep dread of ancient invisible empires because it suggests they are not already everywhere, but it adds a different kind of unease. It implies that silence may be temporary. The stillness of the current sky may resemble a brief calm before a universe that becomes far more structured, more partitioned, and less empty. If that future is real, then the question shifts again. The issue is no longer simply why the cosmos looks silent. It becomes what kind of expansion, if any, intelligence tends to produce once it finally escapes its nursery worlds. Between berserker logic and grabby timing, Section 7 places the paradox on a larger stage. The galaxy may be empty because aggressive machines once swept it, or it may be empty because the great age of outward-moving civilizations has only just begun. In the first picture, silence means something terrible has already happened. In the second, silence means history has not yet fully started. Both possibilities preserve the same central pressure. If enduring civilizations exist and if expansion is even moderately feasible, then the emptiness around Earth cannot remain a trivial fact. It becomes a clue about sequence, about policy, about whether intelligence tends to secure the future by erasing rivals, by spreading openly, or by appearing only now at the leading edge of a universe that is still more unfinished than it looks. For decades, The search for extraterrestrial intelligence rests on a very human assumption. If another civilization exists and wants to be known, it will send a signal. More specifically, it will send a signal in a form that human instruments can recognize as deliberate. This is how the first serious searches are built. Radio telescopes sweep across the sky, not because radio is the only possible language of technology, but because it is one of the first that humanity itself learns to produce on large scales. A narrow-band radio emission, concentrated into a slim slice of frequency space, stands out against the broad natural hiss of stars, gas, and cosmic background noise. Nature tends to be messy. Intelligence, at least in human engineering, often appears as order. That contrast becomes the guiding idea. Search the sky for order where only noise should be. It is a reasonable beginning, but it contains a hidden limitation from the start. Radio waves spread. Unless they are tightly focused, they thin out across distance until even a strong transmission becomes almost impossible to distinguish from the background. Earth itself provides the cautionary example. The planet has been leaking radio and television signals for roughly a century. Yet those emissions weaken quickly as they expand outward, at interstellar range. Even a technologically sophisticated observer might struggle to notice them, unless it is listening with enormous precision and good fortune. The strongest intentional message humanity has sent, the Arecibo broadcast of the 1970s, is famous in cultural memory. But even that signal does not guarantee detectability across meaningful galactic distances. The implication is quietly serious. A galaxy could contain many civilizations at roughly the human level of technology, and almost none of them would be easy to hear. Silence in the radio band may say less about absence than about the weakness of the chosen method. The problem grows deeper when the direction of technological development on Earth is considered. Early industrial civilization is loud in radio because it is inefficient. It floods the environment with broad, wasteful transmissions. Over time, communication becomes narrower, more targeted, more digital, more buried in fiber, more difficult to distinguish from natural noise at a distance. A civilization may grow more advanced and less detectable in the very medium humans first choose for listening. If that pattern generalizes, then radio astronomy may be most likely to catch a society only during a brief and awkward stage, after it becomes technical, but before it becomes quiet. That window could be small. In that case, the search may not be missing civilizations because they are absent. It may be missing them because it is listening for the equivalent of a phase they passed through long ago. This is why the field gradually broadens from radio messages to techno-signatures, the larger class of evidence that technology might leave behind whether or not anyone intends to communicate. A civilization does not need to speak to be visible. It may alter a planet's atmosphere, illuminate its night side, generate unnatural heat, reorganize matter in orbit, or produce long-lasting structures that affect the light of its star. The search then changes in character. Instead of listening for a greeting, astronomy begins looking for disturbances, persistent patterns, side effects, traces of industry written into the energy balance of a system. It becomes less like waiting for a phone call and more like studying the skyline of a distant city through a fog, hoping that some feature of the light cannot be explained by nature alone. One of the oldest and most striking ideas in this category is the Dyson sphere, though the name can mislead. The original concept does not require a solid shell around a star. It can just as well mean a swarm of orbiting collectors, habitats, stations, and energy-gathering structures. The point is scale. A civilization that continues growing may eventually draw on a meaningful fraction of its star's output. If it does, the system should look odd from afar. Visible light from the star may be partially blocked, while waste heat from all that energy use should be re-radiated in the infrared. Modern infrared surveys, including work from missions that scan the sky at these wavelengths, give astronomers tools to search for stars that appear dimmer than expected in visible light and hotter than expected in infrared. No confirmed Dyson structure has been found. That matters. But the fact that astronomy can even frame the search in observational terms marks a major shift. The paradox is no longer approached only through silence. It is approached through missing kinds of heat, missing kinds of light, missing kinds of normality. Against that background, certain anomalies become unusually magnetic. The most famous early example arrives in the late 1970s at the Big Ear Radio Telescope in Ohio. The instrument is part of a serious search program, collecting streams of data that are later reviewed by hand. In one stretch of output, a signal appears that is so far above the background and so neatly concentrated in frequency that it immediately stands apart. It persists for the full time a fixed telescope beam can hold that patch of sky, about 72 seconds, then disappears. The volunteer who reviews the printout marks the event with the word that later becomes attached to the signal itself. The WOW signal enters scientific history not because it proves anything, but because it refuses to fit comfortably anywhere. It appears near the hydrogen line, a frequency long imagined as a natural universal landmark for any radio-capable species. It is strong, narrow, and singular. Follow-up observations over decades fail to recover it. Natural explanations are proposed, including later suggestions involving cometary hydrogen, but none settles the matter cleanly. The signal remains what science often dislikes most, not evidence of aliens, not explained away, simply unresolved. That status is more important than it first appears. A single unexplained signal is not enough to overturn caution, but it does something subtler. It demonstrates that the sky can produce events that match expectation well enough to unsettle, yet not well enough to confirm. It leaves behind a tone rather than a conclusion, a suspicion that the border between ordinary astronomy and possible technology may not be sharp. The search is not only for certainty, it is increasingly for patterns that force better questions. In the 21st century, one star does exactly that. Known to astronomers by a catalogue number, but widely remembered through the name of the researcher who leads its investigation, Tabby's star becomes one of the most discussed oddities in modern observational astronomy. The Kepler mission, designed to watch thousands of stars for the small regular dips caused by planets crossing in front of them, finds in this object something entirely different. Instead of neat periodic transits, the light from the star undergoes irregular and sometimes very deep dimming events. At certain times, the drop in brightness is far larger than a Jupiter-sized planet could cause, and the pattern does not repeat with the strict regularity expected from a simple orbiting body. The effect is messy, asymmetrical, and difficult to reduce to a familiar template. For a brief moment, the public imagination leaps to the most dramatic explanation. A megastructure, perhaps a partial Dyson swarm, moving in fragments across the star. Scientists do not embrace that conclusion, but they do take the anomaly seriously. That distinction matters. The object is worth study not because extraordinary claims are exciting, but because the light curve genuinely resists easy classification. Over time, the leading explanations turn back toward nature, especially clouds of dust produced by disintegrating bodies or complex debris fields. Those explanations account for much of the observed behavior, especially the way the dimming changes across different wavelengths. Yet even with natural models preferred, the episode leaves a lasting impression. It shows that a real star can produce exactly the kind of disturbance a technosignature search would be trained to notice. The instruments are not searching blindly. They're capable of finding things strange enough to matter. The same is true, in a different way, of fast radio bursts. These are millisecond flashes of radio energy arriving from far beyond the Milky Way, some of them releasing in an instant as much energy as the sun emits over days. For years, they seem almost absurd, too brief and too intense to fit comfortably into established categories. Then the catalogue grows. Some repeat, some show cycles, some seem tied to extreme objects such as magnetars, highly magnetized neutron stars with violent physical environments. A local burst connected to a magnetar in the Milky Way helps anchor at least part of the mystery in known astrophysics. Yet the full story remains broader and stranger than a single explanation comfortably covers. The significance for the Fermi question is not that fast radio bursts are alien messages. They almost certainly are not in any simple sense. Their significance lies in the lesson they carry. Each new observational window reveals phenomena that once would have seemed unbelievable. The sky is capable of generating signals far stranger than human expectation. That means two things at once. It warns against rushing to artificial explanations, and it warns against assuming that current categories are complete. By now the search has become more complicated than the early dream of a clear greeting from another star. Astronomy listens, but it also scans for altered atmospheres, excess heat, unnatural orbital structures, odd dimming patterns, and other persistent traces. It knows that most anomalies dissolve into natural explanations when better data arrives. It also knows that not all mysteries vanish on schedule. The silence remains, but it is no longer uniform. It is interrupted by events that flicker at the edge of interpretation, enough to remind science that absence is not always simple. Some signals arrive once and never return. Some stars dim in ways no one expects. Some bursts erupt from across the universe and challenge the categories designed to contain them. None of this solves the paradox. It deepens it, because the more carefully the sky is watched, the more it reveals a second truth alongside its emptiness. It is not only silent, it is full of things that remain just strange enough to keep the question alive. Even if intelligence survives, even if it avoids self-destruction, and even if it wishes to move outward, the universe still imposes a final layer of resistance that is easy to underestimate from the safety of imagination. Interstellar space is not impossible to cross, but it is brutally indifferent to biological timescales, engineering limits, and the cost of error. The nearest stars are close only in poetic language. In physical terms, they are separated by distances so large that every ordinary intuition fails. A craft travelling at a significant fraction of the speed of light still needs years to reach even the nearest stellar system. A slower vehicle may need centuries. A civilization that intends to move through a galaxy must therefore solve not one problem but many at once. It must generate enormous energy, shield itself from collision at extreme speed, maintain continuity over durations longer than many empires have ever lasted, and do all of this without assuming that the journey itself will destroy what it sets out to preserve. The first barrier is energy. To accelerate even a modest payload to a tenth of light speed demands a quantity of energy so vast that human civilization still treats it mostly as a thought experiment. The problem is not only building powerful engines, it is supplying and controlling energy on scales that make chemical propulsion look almost decorative. Nuclear concepts help in theory, whether fission, fusion, or more speculative beam-driven sails. But each opens its own engineering abyss. Fuel has mass. More mass demands more fuel. Shielding adds mass. Life support adds mass. Redundancy adds mass. The familiar rocket equation turns from inconvenience into punishment. It is one thing to reach orbit. It is another to cross interstellar dark without a supply chain, without rescue, and without any room for ordinary failure. Then comes collision. Space between stars is not empty in the clean cinematic sense. It contains gas, dust, grains, and small bodies, all sparse on human scales yet dangerous when encountered at relativistic speeds. A particle no larger than a grain of sand can deliver catastrophic energy if struck by a craft moving fast enough. Shielding against that risk is not a detail. It is one of the central design problems of interstellar motion. Even autonomous probes would need solutions that humanity has not yet demonstrated. Crewed travel becomes harder still. The farther a civilization tries to reach, the more every tiny object in the dark becomes a potential weapon made of ordinary matter and relative velocity. Time is just as severe. Even if the engineering can be solved, the culture behind the mission must persist through the wait. A species may launch probes and still never hear back within the lifespan of those who sent them. Colonies separated by light years would live under communication delays too long for ordinary political unity. Interstellar civilization, if it can exist, would not resemble the tightly linked societies familiar on Earth. It would be loose, delayed, fragmented by time itself. This matters for the paradox because it weakens one of the oldest assumptions. A civilization does not automatically spread through the galaxy just because it can. It may conclude that the costs are too high, the delays too long, the returns too uncertain. The galaxy may be full of worlds that produce intelligence yet remain homebound, not from lack of ambition, but from respect for physics. That explanation has a quiet plausibility. It allows many civilizations to exist without meeting. It turns the silence into confinement rather than emptiness. Yet even this restraint does not erase the strangeness of what has already entered the solar system from beyond. In the autumn of the 21st century's second decade, astronomers detect the first confirmed interstellar object passing through the inner solar system. It is named Oumuamua, a messenger arriving first. At first it seems like exactly the kind of object theory predicts should occasionally appear, a body ejected from another stellar system long ago, wandering through interstellar space until chance brings it near the Sun. That alone would have been remarkable. Then the measurements begin to accumulate, and the object refuses to behave with the comforting normality of a simple comet or asteroid. Its brightness changes dramatically as it tumbles, implying an extreme shape unlike familiar solar system objects, either unusually elongated or perhaps flattened in a way difficult to pin down from limited data. More troubling is its motion. As it recedes from the Sun, it accelerates slightly beyond what gravity alone should produce. Comets can do this through outgassing. When sunlight heats volatile material and jets of gas push the body like weak thrusters. But astronomers find no clear coma, no visible tail, no obvious signature of the ordinary process. Natural explanations are proposed one after another. Hydrogen ice, nitrogen ice, a highly porous structure, a thin shape susceptible to radiation pressure. Each accounts for some features and struggles with others. Most researchers continue to prefer natural possibilities, and that caution is justified. But the deeper fact remains. The first known interstellar visitor is not comfortably ordinary. It passes through once, leaves too quickly for close inspection, and remains unresolved. This does not prove design. It proves something almost as important for the mood of the paradox. Human beings are now living at a stage when objects from other star systems can physically enter the observational field, and the first such case arrives carrying properties that remain debated years later. A second visitor, Borisov, behaves much more like a standard comet, which only sharpens the contrast. One object looks normal, one does not. The universe offers both familiarity and disturbance in the same category, as though reminding astronomy that interstellar space is no longer only a distant abstraction. It occasionally comes through the neighbourhood and leaves questions behind. Yet the paradox may become stranger still when intelligence itself is examined more carefully. The search often assumes that minds, once they arise, build technology that becomes visible at a distance. Earth encourages that assumption because humanity does exactly that. But Earth also provides counterexamples large enough to matter. Dolphins, elephants, corvids, and octopuses all display forms of cognition that would once have seemed extraordinary. They solve problems, remember, communicate in structured ways, and navigate rich social worlds. None of them build radio telescopes. Intelligence and industrial civilization are not synonyms. A world may host minds while remaining externally quiet. This matters because many potentially habitable environments may not even permit a route toward fire, metallurgy, or electronics. The icy moons of the outer solar system sharpen this point. Europa almost certainly hides a global ocean beneath a shell of ice. Enceladus vents material from a subsurface sea that shows signs of internal hydrothermal chemistry. Titan offers lakes and atmospheric chemistry unlike anything on Earth's surface. These worlds are compelling because they widen the idea of habitability. They also expose a deeper limitation: a civilization evolving beneath kilometers of ice in a sealed ocean without open sky, stars, or access to fire may never develop the physical path that leads to space-facing technology. It may become intelligent in its own medium and remain forever enclosed by the structure of its world. It may possess language, memory, even forms of science adapted to fluid darkness, yet never know that a galaxy exists above the frozen roof. Such beings would be silent not by choice, not by fear, not by extinction, but by architecture. Their world would hide the cosmos from them. Their tools would evolve in water. Their myths, if they had them, might never include stars. Their physics might be profound and still remain local. Humanity searching the sky would learn nothing from them, while they lived out full histories in a sealed internal universe. Once this possibility is admitted, the pool of detectable civilizations shrinks sharply. Habitable does not mean visible. Living does not mean communicative. Intelligent does not mean technological in the specifically human sense. Then there is the final complication, perhaps the quietest and the most difficult. Even where intelligence does become technological, there is no guarantee human beings would recognize the form it takes. Search strategies are built on human ideas of structure, prime numbers, narrow band signals, geometric regularity, atmospheric imbalances, waste heat. These are sensible markers, but they are still projections of human cognition and human engineering. Another intelligence may process the world through very different sensory channels, timescales, or concepts of representation. Its signals may be embedded in modes humans do not monitor or do not yet know how to separate from background nature. Its artifacts may appear to human instruments as irregular dust, noise, or something so unfamiliar that it never enters the category of evidence at all. Earth again offers a humbling comparison. For long stretches of scientific history, non-human communication is judged against human language and therefore underestimated. Over time, more careful frameworks reveal that prairie dogs encode detailed information about threats, bees communicate distance and direction through movement, and whale song carries layered structure across vast distance through water. Complexity is present long before it is recognized. The failure is not in the signal, it is in the frame used to read it. Scaled up to alien minds, that warning grows severe. The Fermi Paradox may partly be a paradox of perception. The sky may look silent because human beings are listening for minds that resemble their own. So Section 9 gathers several quieter answers together. Travel may be far harder than imagination admits. Visitors may be rare, ambiguous, and gone before certainty is possible. Minds may thrive in places cut off from the stars. Others may speak in forms that do not register as speech at all. Under these conditions, the silence is no longer a simple lack. It becomes layered by physics, by habitat, by anatomy, by cognition, and by the limits of the observer. The galaxy may still be mostly empty of visible civilizations, or it may be full of unreachable, unrecognizable, or sealed-off intelligence that never steps into the narrow corridor human searches can illuminate. The question remains the same, but its edge changes. It is no longer only where everybody is. It is whether they can cross the dark, whether they can ever face the sky, and whether human beings would know a mind had passed nearby, even if it already had. At the far edge of all these explanations, where biology, astronomy, and speculation begin to overlap, the paradox takes on its most intimate form. The question is no longer only why the sky looks silent. It becomes whether the answer has been present from the beginning, hidden not in distant stars, but in the timing of Earth, in the chemistry of life, and in the possibility that humanity is not late to a crowded universe at all. It may be early, very early. That possibility sounds at first like arrogance, but the argument behind it is more restrained and more unsettling than that. The universe is ancient, yet it is not uniformly ready for intelligence from the start. The earliest stars contain almost none of the heavy elements needed for rocky planets, complex chemistry, and the long, slow experiments of biology. They blaze, die, and seed the cosmos with carbon, oxygen, silicon, iron, phosphorus, and the other ingredients that later generations inherit. Only after many such cycles do planetary systems like the solar system become common enough for Earth-like worlds to emerge. Then even after a suitable world forms, billions of years may still be required before complexity and intelligence appear. That sequence matters. It means the age of the universe alone is misleading. A universe can be old and still not yet mature everywhere for minds. Earth forms only after the galaxy has already been chemically enriched by earlier stars. Then life, if it begins quickly, still remains simple for most of the planet's history. Complex multicellular forms arrive late. Human technological intelligence arrives later still, almost at the edge of the available timeline if the whole chain is considered. Under this reading, the silence may not mean that civilizations are absent because they fail. It may mean the universe has only recently become capable of producing many of them. Humanity may stand near the front of that wave, not because it is special in essence, but because the cosmic schedule itself places intelligent life close to the beginning of its possible era. This idea changes the emotional shape of the paradox more than it changes the facts. The same empty sky remains overhead, but instead of reading it as the aftermath of extinction or concealment, it becomes possible to read it as a kind of dawn, not the dawn of the universe, which is long past, but the dawn of observers capable of understanding it. If that is true, then the stillness of the Milky Way is not the stillness of a ruined city. It is the stillness of rooms not yet occupied. Humanity would then not be searching for predecessors. It would be standing near the first opening of a future that has not fully started. Yet this possibility does not remove the stranger alternatives. It only sits beside them. One of those alternatives begins with life itself. The origin of life on Earth remains unresolved at the mechanistic level. Science has many candidate pathways, many partial successes, many plausible environments, but still no complete account of how chemistry crosses into biology. That gap has long tempted more radical interpretations. One of the most persistent is directed panspermia, the idea that life on Earth may not have begun here unaided, but may have been seeded deliberately by an older civilization. The proposal remains speculative and controversial, But it is not built from mysticism. It begins with a simple discomfort. Life appears on Earth relatively early after the planet cools. The genetic code is universal across all known organisms. Every living thing on Earth shares the same deep molecular language. The standard explanation is common ancestry, and that remains the scientific consensus. But a more unsettling possibility shadows it. If a civilization sought to spread life widely through the galaxy, microbial seeding would be one way to do it. The biosphere of Earth would then not be a local accident alone. It would be an inheritance. Nothing confirms that. Still, the idea has power because it reverses the search. Instead of looking outward for a message, it looks inward at the architecture of life itself. DNA is dense with information. It is stable enough, under the right conditions, to carry patterns across immense time. Some researchers have wondered whether a civilization could bury a marker, a mathematical structure, or some other non-random pattern within biology as a durable archive. No confirmed such signal has been found. But the mere possibility opens another door in the paradox. If life is seeded, then finding life elsewhere would not necessarily mean multiple independent origins. It could mean branches of the same deep experiment scattered through space. The silence of the sky would not imply isolation. It would imply ancestry too old to recognize easily. An even stranger turn appears when the question of observation itself is pushed to its limit. Humanity knows the distant universe through signals. Light arrives, radio waves arrive, gravitational distortions arrive, and from these arrivals a picture is built. That picture is vast, rigorous, and increasingly precise, yet it remains mediated. No one has visited another star. No one has tested the reality of the wider cosmos by direct encounter. This fact opens the door to the planetarium idea, the suggestion that what humanity sees may be filtered, managed, or incomplete in a more fundamental sense than ordinary ignorance. In its stronger form, this becomes close to the simulation argument. Reality may be computational, local, or selectively rendered. In a softer form, it becomes something like a cosmic stage set, not necessarily a digital illusion, but an environment whose observable signals have been shaped so that young civilizations perceive a quiet universe, whether or not it is truly empty. Scientifically, these ideas are weak in the strict experimental sense because they are difficult to test. That weakness has to be acknowledged. But as philosophical pressure points inside the paradox, they do something important. They remind science that all conclusions about cosmic loneliness are made from inside a limited observational bubble. If the inputs are incomplete, manipulated, or fundamentally constrained, then even a careful picture of the sky may still be missing the decisive layer. The silence would then not be evidence that nobody exists. It would be evidence that the observer has reached the edge of what the system allows it to know. Against these speculative horizons stands a newer, more grounded development. Humanity has begun to study exoplanet atmospheres in enough detail to search for chemical imbalances that might hint at life. The James Webb Space Telescope has made this possible in a way earlier instruments could not. When a distant planet passes in front of its star, some starlight filters through the atmosphere of that planet before reaching the telescope. Molecules in the atmosphere absorb specific wavelengths, leaving a pattern that can be read. This technique has already revealed carbon dioxide, water vapor, and other compounds in alien skies. In a few debated cases, astronomers have reported hints of molecules that on Earth are strongly associated with biology, including on the planet known as K218b. None of these cases is settled. The signals are weak. The interpretation is difficult, and abiotic alternatives remain under study. But the importance does not depend on any one planet being confirmed alive. The importance is that the search is leaving pure theory behind. For the first time, Humanity possesses instruments capable of testing whether life alters distant atmospheres in detectable ways. That shift matters because it sharpens every branch of the paradox at once. If more and more habitable worlds appear chemically dead, the case for rarity strengthens. If biosignatures begin appearing often, then life is common and the mystery moves to later stages. If one day a technosignature is found, an unmistakably artificial pattern written into light or heat, the paradox changes completely. The silence would fracture. If nothing is found after decades of deeper searches, the stillness would become harder and harder to attribute merely to weak instruments. Either way, the coming era does not close the mystery, it intensifies it, and there remains one final possibility, perhaps the most difficult to rest with because it asks the least and implies the most. Humanity may simply be first, or among the first, in this region and this age of the universe. No hidden watchers, no galactic quarantine, no ancient machines, no message encoded in DNA. Only a cosmos that takes a very long time to prepare the conditions for minds, and a species that appears close to the beginning of that window. In that case, the Fermi Paradox is not solved by finding what silenced everyone else. It is solved by realizing that almost no one else has arrived yet. The galaxy is quiet because the story is young, but even that answer refuses to settle into certainty. Too many doors remain open. Life may be widespread and sealed away beneath ice. Intelligence may be abundant and technologically mute. Civilizations may flare and fail. They may hide. They may watch. They may travel in ways no human search strategy yet imagines. The sky does not close around any one explanation. It only keeps returning the same unbearable combination of richness and absence. Stars everywhere, planets everywhere, chemistry everywhere, and still no clear second voice. Whether that silence is a warning, a veil, an early morning, or the natural state of a universe where minds are almost impossible, it leaves one fact unchanged. Earth is already inside the question. This search has never been only about others. It has always been about what kind of thing manages to appear in a cosmos this large and remain long enough to ask why it seems so empty. For now, the silence remains intact. Telescopes continue to widen their reach. New surveys catalogue more planets, more atmospheres, more odd bursts, more dimming stars, more objects moving through the dark between systems. Each year adds detail, but detail does not always bring closure. Sometimes it does the opposite. Sometimes the universe becomes more knowable and less familiar at the same time. A signal lasts for only seconds and then never returns. A star fades in patterns that seem too structured, then slips back toward dust and uncertainty. A visitor from interstellar space crosses the solar system once, behaves strangely, and is gone before any close answer can catch it. Biology reveals how much had to go right for Earth to become a world with eyes and memory and tools. Physics reveals how hard it may be for any mind to cross the gulf between stars, and still, none of it is enough to quiet the central unease. The question endures because it refuses to stay in one place. It begins in astronomy, then moves into chemistry, then into evolution, then into risk, then into the limits of perception itself. It asks whether life is rare, whether intelligence is fragile, whether civilizations are brief, whether the galaxy is hiding, whether the timing is wrong, whether the search is naive, whether the answer is already written into the structure of life on Earth, or into the structure of reality deeper still. Each possibility explains part of the silence and leaves another part untouched. So the sky remains what it has always been: crowded, ancient, and strangely withholding. It offers enough to suggest that life should not be alone, and too little to say where the others are. Perhaps the universe is waiting. Perhaps it is warning. Perhaps it has already spoken in forms not yet understood. For now, there is only the stillness between the stars, and one small world listening from inside it, not knowing whether it is late, early, hidden, watched, or first.